We began to discuss last time the foundation of dynamics, the variational principle, the principle of least action. And we saw that when we formulate dynamics in this way, namely when we postulate that there exists, that by dynamics we mean some system characterized by coordinates which depends on t. There could be many different versions of these coordinates for different systems. It could be angles or position of center of mass and so on, or position of each particle. We looked at many particles. So, and the problem of dynamics, the problems of dynamics are twofold. First of all, we need to know the basic equations for these quantities. And secondly, we need to solve this, to know how to solve these equations. And as we discussed, kind of a miracle is that all known dynamical systems in nature, they have their origin in the variational principle. So what does that mean? That means that there exists a quantity which usually is called S and called action, which is a functional of those trajectories. And the equations of motion are they can be formulated as a condition that the first variation of the action is equal to 0. So I shall not repeat our definition of the first functional derivative, but it's basically that the first derivative in the function space vanishes, and that gives you the equations for those xi of t. Then we and the simplest example, it is a kind of a postulate. There is no way to derive it from something else. Well, you can derive it from more sophisticated quantum mechanics, but then you have to decide why quantum mechanics is in this way. This is a highly non-trivial statement by itself. The fact that the system follows from the variational principle is highly non-trivial. And we saw last time that for such systems, there exists what is called Noether theorem, which associates symmetries and conservation laws. And I remind you very briefly, in a couple of minutes, the idea of the derivation. We said, let's suppose that the action is translation invariant, and let's perform infinitesimal transformation. But we do it so if we add some constant a. If we add some constant a, the action doesn't change. That's, we assume, is the consequence of symmetry, that it is symmetric under translation. And of course, there are hundreds of examples of such systems. But then we said, in order to discover the connection between symmetries and conservation law, let's gauge this symmetry. Gauging means that you make the parameter, let's see how the action changes when the translation parameter is time dependent. And by the way, of course, the same strategy applies to all symmetries, as we discussed. It could be translation are the simplest, but there are rotations and so on. And then we said that since if we look at the variation of the action, it should have the form of some quantity which depends on t, and which is a function of which depends on all those xi's, which are calculated explicitly, multiplied by a dot of t. And then we said, let's choose a of t. We integrate from t1 to t2. Let's choose since we want to, when we derive the equations of motion, we always fix initial and final points. So a of t2, a of t1 is let's take it 0. It's not, you see, it's a matter of convenience. It's not that something order us to do this. But let's try this first, and then we'll see what will happen if we relax this condition. Anyway, if you have this condition, we said we can rewrite it as in this way. And that means, and then from this formula, it follows that this is 0, and a is arbitrary function of t. So what follows from this is that p dot of t is equal to 0. So there are I'm repeating this because it's one of the fundamental things in physics, namely that you have a well-defined and very simple prescription how to associate conservations, in this case conservation of momentum, with symmetry. We have symmetry, we get conservation. And I actually recommend you to go through this very elementary algebraic proof, which is actually there are no complicated formulas, nothing. But there are some small twists of logic which people often miss. So go through this carefully. Now, so when you are asked, okay, but how to find these conserved quantities, the answer is very simple. Just expand the action in this way, and what you get here, the coefficient, is what you need. That's we call it momentum, but we can call it any other name. What is objective is the fact that the coefficient in front of a dot, we gauge this translation symmetry, the coefficient in front of a dot is conserved quantity. And of course, when we do the same thing with rotation, with infinitesimal rotation, the corresponding quantity is angular momentum. And we also started to discuss the notion of energy, namely the symmetry when we replace when we discuss energy. We have to look at x of t. It's associated with a gauged translation of time. We call this function f. So it's just reparametrization of time. And we followed the same. We noticed that by simple calculation, if we look at the action of a simplest system, we have, after reparametrization, S twiddle is we have to, when we look at this thing, we get v of x. Let's start with this term. We substitute it by this thing. We get dt, and we get, it's the second piece of the action, we get integral v of x of f 1 over f dot dt. So the action naturally changes. And when f is, when A is not gauged, when it is independent of time, f dot is 1, and it doesn't change. And the first term, this term contains dt in the numerator, this term contains dt in the denominator, and as a result of this, I will not repeat, of course, the change of variables. We get kinetic energy. I shall not repeat it partly because we will now develop a more general point of view about these things. So we have dt in the numerator, so we got f dot. Excuse me, here is df, of course. And the result of expanding in A, we get energy, which is the coefficient in front of A dot. Energy is, and we know that that if the trajectory satisfies this, then this thing is time independent. Energy is time independent. That was basically what we discussed last time. And now we will strongly generalize and improve it. But before I come to this, let me give you one example. So we have, let's take, to check the ideas, let's take a harmonic oscillator with friction. The equation of motion, the Newton equation for this harmonic oscillator with friction is just that. Now let me ask you, if this system is translation, does it have time translation symmetry?
Yeah.
Yes, it does. Indeed, if we have x of t plus a, nothing happens, of course, when you substitute it. So if x is a solution, x twiddle is also a solution. But now we are in trouble, because is there a conserved energy for this oscillator? Well, you have this oscillator which moves with friction, and what if you solve it? What would be asymptotic solution? What x of t how it behaves at large time? Think physically, not you don't have to solve this. Yeah, sure. It's just will stop because of friction. So if there was some energy in it at the beginning, there will be no energy at the end. And it seems that it contradicts to what I was just saying. So try to think of way out of this paradox. I was just proclaiming at the beginning that if you have time translation symmetry, then you have energy which is conserved. All this great, and then the simplest counterexample seems to demolish all this logic, except it does not. But there is only one logical conclusion which can I didn't make any mistakes in this derivation. Let's postulate it. That will not be always so about my derivations, but in this case, let's assume that everything is right. Then you must make a single possible logical deduction from this.
This doesn't solve the action equation?
Say it again?
That this equation is not a solution to the action equation.
That's right. That's right. The answer to this question is, which we will work out now, is that this equation is not derivable from the variational principle. So that's a first indication that of what I was saying before, that simply the statement that there is variational principle, even when you don't know the action, is a huge amount of information. So let's try to understand what happens. Let's analyze this simple example a little more. When we looked at the, and it will be actually, this discussion will be instructive and useful. When we have this action, let's forget about the potential. We did this variation. We integrated by parts, and we got mx double dot delta x dt, and so on. Now, let's try to find the action which and in this way, you see, we reproduced the first term, right? We have we varied this thing, and coefficient in front of the delta x was just what we needed. Okay, now look at this and try to figure out what kind of term in the action would reproduce this second term. How to modify there? Let's try to. It's something you always have to do with new concepts. You just try to deform it in this direction, in that direction, see how it works, why some coefficients cancel, and so on. That's basically how people make progress. So let us try to find, I want your suggestions about the term in the action which would give us x dot. What should you modify here to get something like x dot?
X dot.
Yes, let's try it. Let's try it. It seems everything is going fine. This is the third piece in the action. Indeed, we get delta S3, which will be proportional to delta x, x dot, plus x delta x dot. So we seem to be getting almost what we need. But there's one problem. What happens with it when you integrate by parts? The second term, we always have to reduce the expression to the standard form when then the variation is proportional to delta x. That's how we define variational derivative or functional derivatives. So we integrated by parts. What happens? the two terms cancel, indeed. Why it could have been foreseen that they will cancel. Why is that? What happened? What is typical for S3, which we should have, in hindsight, we should have known that variation of it will cancel. Why? What is so special about this functional that it has zero variation?
I mean, if you use the Euler-Lagrange equations, ddt of dl dx dot is the same as dl dx.
Yeah, but that's what we just did. I want a little more than what you said is right, but I want something more.
You can integrate it directly.
You see, what's happening here is that let's rewrite this term as then we take the integral and we get as a result, you see that we don't vary endpoints. At the endpoints, x is fixed. When we vary x of t, it doesn't depend on x of t. It's a complete derivative. So when the functional contains a complete derivative, it doesn't participate in the game. You don't get anything in the when you vary the things in the middle. But we're not done yet with this example. Let's try to think of some system. See what happens. So once again, this doesn't contribute to the equation of motion, and that was the only term which could have contributed, because this term is complete derivative. Now let's suppose we have several components, xi's, say 2, starting with 2. Can you give me an example of this action which would give us first order term in the equation? In this case, it is possible to generate the first order term. First order, I mean, when the term with first derivative from the variation of the action. So let's suppose you have x1 and x2. You have which would correspond, for example, to a harmonic oscillator in a plane. It has x1 coordinate, x2 coordinate. Suggest me some action which would generate equation, which would generate contribution. Something very similar, but we already understood that in order to have first derivative, you need the action of this type. So, some example. For instance, if we simply write down x1, x1 dot plus x2, x2 dot, that's no good, because it's the same as this example. This is a complete derivative. But if you play around with it a little bit, you will get something useful. So this is a useless stuff. How about this? What do you think? Is it useful or useless? By useful, I mean, does it generate equations of motion or it does not? So how about this term? Huh?
Also doesn't.
Yeah, why? You're right.
Because derivative x1, x2.
Yeah, it's just a derivative. Okay, but now,
You change plus to minus.
yeah, that's, some great discoveries are made by changing plus to minus. So let's take this thing. And then when you vary this thing, you add it to the action of harmonic oscillator, and you will get the equation, not surprisingly. That's what you get when you add this term to the action. And what I want from you now is, and now, will this system have conserved energy or not? That's the first question. That's, after our discussion, it's kind of a trivial question. Of course, it must conserve energy because we derived it from the variational principle. So it does. Now, what kind of physics it describes? What this force, with this extra force related to velocity, what could it be? We will encounter with such forces in many cases, in several fields, but there's the most straightforward and elementary case, which I want you to. You see something funny. This, if you interpret it as a force, the one component of the force is x2 dot, the other component is minus gamma x1 dot. So it immediately brings us some idea of some torque or something like that. So what it should remind you something.
Magnetism?
Yes, it is a charged particle moving in magnetic field. And this is the Lorenz force. Now, when you have, in this case, we have a plane, it's 2 dimensions. We have magnetic field perpendicular to the plane. And we have a charged particle on which you have 2 types of forces. It's an oscillator, but there's a charged particle at the end of the spring, of this spring, and so we can actually drop, if you drop it, when we get simply particle in magnetic field, which how a particle moves in magnetic field, charged particle. Suppose you have a plane, you have this magnetic field piercing the plane, and you have a free charged particle on a plane. How it will move?
Just in a circle determined, whose radius is determined by the strength of the magnetic field.
That's right. That's right. And you see, indeed, suppose you have this particle, and the force which acts, if this is its position is x1, the force acts in direction x2. And it makes it rotating. We will actually, there will be many cases like that later in this course, and we will, but you probably can even now look at the solution without omega. You just look at the solution and discover. We will return to this. The reason is that tornadoes and vortices move very similarly in hydrodynamics. and then we will be discussing this matter. But at this point, all I was interesting. Yes, by the way, although it is how to explain that energy is conserved here. Now you have these forces which acts on this. Nevertheless, energy is conserved. These forces don't work, don't produce work. Why? They are perpendicular. Lorenz force doesn't produce work, and indeed, when you multiply it by dx1, you will get. You obviously see that the force is perpendicular to the velocity here, and as a result of it, it cannot generate work. That's why energy is conserved. So, although it is the first time derivative, first order time derivative, nevertheless, it has completely different meaning than friction. You see, friction forces, they really work. The Lorenz forces don't. One more comment about this example, which is, how about time reversal? Is there time reversal when we talk about this system with friction? So I'm asking this question. Let's take this equation and let's film this thing and then let it go backward. What do you think? Try to think both physically and mathematically. First, physically, in terms of this movie, which you filmed of this damped harmonic oscillator. Can you distinguish between the movie which goes backward and the movie which goes forward? So of course you can, because in the right movie, this particle will start moving oscillate slower and slower and slower. In the backward movie, it accelerates. It starts moving faster and faster and faster. So obviously there is no time reversal symmetry. What does it mean? How you see this mathematically? Physically, it's obvious.
The first derivative would be
Right. So we take x of t to be x of minus t. That's our attempt at generating the new solution. And you immediately see that this term doesn't change sign, while this does change sign. So this term with first derivative actually breaks time reversal invariance. Okay. Now, so it breaks time reversal invariance, and also it breaks variational principle, conservation of energy. Now, how about this example?
It's just an indice exchange when you also flip time.
Yes.
And it rotates the other way.
That's right. Yes, yes, yes. All this means that under time reversal, magnetic field should change sign. And indeed, it rotates. What you said is absolutely correct. It rotates in the opposite direction, and indeed, these terms change sign. What's interesting, though, is that energy is still conserved here, despite time reversal breakdown. here we break down time reversal and energy, and so now let's go from these examples to slightly more general things. Namely, well, before we go to more general things, let's try to understand in a more mathematical way. There's an interesting question to be asked here. Namely, you are given some equations of motion, some equation of motion. How to decide whether it's derivable from the variational principle or not? Of course, you can proceed by trials and errors, but there is something better which can be done. In particular, how to prove, how to see that if we have, there is no such, let's call this action as we called it S3. The question is how to see that it is impossible to find the action like that, or more generally. You see, this is simple equation. Here we understand everything. But in practice, you can encounter with something quite complicated, and it will not be clear whether you simply cannot find the action, but it exists. It may be too complicated, but or it's impossible to find the action. And to understand how to resolve such questions, I shall go to discrete case. Discretization, when you are puzzled, is always a good idea. Some temporary discretization. Let's take discrete time. And what will mean, what will be the discrete analog of this equation? As we discussed several times, we now have variables xt, x1, t is discrete time, so we discretize time. And the action is a function, is some function of these guys. And this relation would mean, what would be the discrete analog of this relation? The left, what would be, let's start with the easy thing, the left side of it. Well, that we discussed several times already. What is the discrete analog of a functional derivative? What? It's partial derivative with respect to xt. And what would be natural to put at the right hand side? What is the time derivative in discrete case?
X sub t minus x sub t minus 1.
Correct. So we're trying to solve this equation. Now, what do you think? First of all, is this equation solvable? And secondly, how to in generally decide whether it's solvable or not. Without this term, what will be the solution of this equation? Huh?
1/2 xt squared.
Yeah, it will be the 1/2 of the sum over t xt square. In this case, if we take this, delta s partial ds3 dxt will be xt. Now, if you if you try this second term, then you will be in trouble because if you write down, well, I think I will leave it for you to check yourself. But
What does this mean at the boundary? When t equals 1?
let's be far from the boundary. Let's forget about the boundary. But indeed, the thing which will happen if you try to solve this is the same, is the discrete analog of this. You will get the thing which depends on the boundary. Was that what you were saying? Probably, no? Anyway, if you try to solve this, you cannot. But there is a very simple criterion for any expression on the right-hand side, whether you can find S3 or you cannot. What is the criterion? It's very simple. The point is, take this second, differentiate this. Suppose that you solve this equation. Take let's call it S. Let's take the second mixed derivative of this. What would be the first term?
Delta t.
Yeah, it will be Kronecker symbol. What will be the second term? It will be also Kronecker symbol, of course. It will be t minus 1s. Now, why it is impossible?
Because swapping them gives a different result.
What?
If we swap the partial with respect to x of t and
Yeah.
with respect to x of s, we get a different answer.
Yes. The point is the left-hand side is symmetric under interchange t and s. The right-hand side is not. Therefore, this equation is impossible to solve. And that gives us, now we can forget about those discretization is like crutches which help you move. But now let's forget about them. Let's throw them away and simply notice. Let's calculate now the second variational derivative, delta x of t, delta x of s, assuming that this equation holds. What's the answer? What is the answer here when you differentiate this guy? This equation means that delta S3 is x dot of t, delta x of t, and we can rewrite it as minus Yeah, well, that's it, and that defines for us. Excuse me, it's. We have to put this, and we have to put delta function of s minus t. So that's again our game with functional. If it was simply x of t, what is this is our functional is the value of x at the moment t. What is this? Again, you can well, it's just the delta function. It's just the delta function. Now, when you differentiate it with respect to t, you get delta dot of t minus s. Now, the delta function is, and of course, it fully corresponds to these discrete versions. The delta function is an even function, while if you differentiate the even function, you get the odd function. And so this, when we differentiate this thing, we get the second variational derivative. So the left-hand side is symmetric, the right-hand side is not. So, and that more or less gives you the prescription in general cases how to decide whether the equation is derivable from the variational principle. Okay, let's. I probably lost a little more time than I intended here. Let's address another question concerning variational principles. How do we find the action? You will see actually then when we learn those things about variational principles, how in many cases they tremendously simplify and the problem solving, and also how they give you a global view on what's going on with a dynamical system. So that's why it is I'm spending a lot of time on discussing this. But you have to get used to them and to variational derivatives and so on. So our question now is why, as I said, we started with the action which was the difference between kinetic and potential energy. And all textbooks begin with this. The question is why is that? Can we understand why it happens? And again, symmetry is the answer. And amusingly, it's easier to begin with, not with non-relativistic dynamics, but with relativistic. In relativistic case, the answers are easier. It's also typical for physics that sometimes it's easier to solve more general problem, to develop some natural language for more general problem and solve them, and then go to some special cases. For instance, in many cases, quantum mechanics is simpler than classical mechanics. And relativistic mechanics is also sometimes it's less. Quantum mechanics is actually, well, we will be talking a little bit about quantum mechanics. Okay, so let's derive the Lagrange function for relativistic particle moving in space-time, and then in non-relativistic limit we will reduce it to the other thing. When we have, I remind you that the basic idea of relativistic symmetry is the following. It was actually how Einstein discovered it. He noticed that it was kind of interesting. He noticed that in a very early age that if you have a light ray and you run with the speed of light near this light ray, you will see a standing wave. But Maxwell equations don't have a solution of standing waves. They only have propagating waves. And the basic and the symmetry of the Maxwell, so Maxwell equations are explicitly not invariant under Galilean transformation. If you make changes, this is the Galilean transformation. Then Newton dynamics is invariant, as we saw at the first lecture, is invariant under these transformations, but not so Maxwell equations. And so the idea of Einstein was to start with a symmetry which is in the Maxwell equation, and the symmetry basically can be understood very easily. It simply the statement that in any frame you have the same propagating wave. In other words, the wave front is given by this expression. When it is 0, you get the spherical wave, or in 2 dimensions, circular wave. And the symmetry in question is this. It's x squared minus c is speed of light. Let's set it to 1. All right, I will put it just like that. This is the invariant expression, and if we are in 1 + 1 dimension, this is the expression which describes the propagation of the light wave. And to find the explicit formulas for transformation, we simply factorize it. And consider the transformation when x plus t goes onto lambda x plus t, x minus t goes to lambda minus 1 x plus x minus t. Very simple. And obviously this will be invariant. Now, to understand the geometry of this transformation, and what we will be doing in a moment, is we will find the Lagrange function which is symmetric under this transformation, which is invariant under this transformation. And that will be the Lagrange function of relativistic particle. And then going to a slow moving limit, we will find the Newton expression. It is, by the way, I leave it to you if you don't know this. It's very elementary to find from here that you can introduce another parameter so that it will be this is just the identical. This is the standard form of the Lorenz transformation, which you'll find it in the elementary textbooks. This is a much more convenient way of doing this, and we will now understand the meaning of this thing. First of all, let's notice that it should remind us something, namely, let's assume that time is imaginary. And then analytically continued back to the real time. If time is imaginary, so let's introduce t equal to I tau. Then what kind of symmetry? We need symmetry, which leaves this invariant. What is geometrical meaning of this symmetry? It's something it's a very simple question, actually. So we transform coordinates x and tau in such a way that some, yeah, go ahead, please.
Length is invariant.
Like what?
The length of.
Yes, and under which, okay, good. Under what transformation the length is invariant? How we call it in geometry?
Rotation.
It's rotation. So it's just two-dimensional rotation. Now, what happens? X plus t changes under this to x plus I tau. And this is the complex variable z. These variables, by the way, which are very useful, they are often called the light cone variables, x plus and x minus t. But for imaginary time, it's just z bar, complex conjugate of z. Now, what is rotation in terms of two-dimensional? We're talking about two dimensions, and we have complex variables. What is rotation in terms of complex variables? What do we do with z? What do we do with x and tau? You know, it's elementary formula like x cosine theta plus tau sine theta and so on. What happens with z variable when you rotate the frame?
E to the I theta.
Yes. When you compare it with this thing, how would you interpret this transformation geometrically? So here we have z transformed like that. Z bar transforms with a minus e to the minus I theta. So what would be how to relate this to this so that it will have some very intuitive and natural meaning? I will help you by changing notation here. I will introduce a new variable which is sometimes called rapidity, which is e to the theta. It should help you to understand the meaning of this transformation. So what is this? We have let's introduce two light cone variables, x plus t and x minus is x minus t, and the Lorenz transformation is x plus goes to e to the theta x plus, x minus goes to e to the minus theta x minus. Well, so what would you say? What is the Lorenz transformation? How to describe it?
It's rotation with an imaginary angle.
It's rotation with imaginary angle, and that's extremely useful idea because it gives you understanding of what geometrically goes on. Okay, so as a result, we can form invariant expression very easily. You just form the invariant expression for rotations, and then you analytically continue time to imaginary time. Well, if originally it was imaginary time, you go back to real time, and that gives you the invariant expressions. Okay, now you can say that there are this space with this invariance. This is the Euclidean space, obviously. While with a minus, when you put a minus here, like here, it is called Minkowski space. And in general, you can always write down something like that. You can always define it like that, with I square being minus 1 in the Euclidean case and plus 1 in the Minkowskian space. But it's very important to understand that the geometry of the Lorenz is extremely simple and intuitive. So this part is well understood. There is, of course, the question why nature selects this minus here, not plus. These minuses, those signs are called signature. So why we have Minkowskian signature in nature instead of Euclidean or something else? Well, that no one knows. Okay, but now we will turn to something which everyone knows, namely the Lagrange function which is Lorenz invariant. Remember, we discussed at some point the invariant functional under rotation. So what was the simplest invariant functional under rotation and translation? By the way, well, okay. So rotation and translation.
Length.
Length, right? Okay, now I want the expression for the action, which will be Lorenz invariant. I now have a space-time. In this case, we have x. It's two-dimensional space-time, but that doesn't matter. In general, you can have four-dimensional space-time, and you have a trajectory in four-dimensional space-time. So when particle moves, it sweeps a one-dimensional trajectory. And I want this expression. So suggest something which will be Lorenz invariant. Let's start with 2 dimensions, although it doesn't change much. Let's do it in 2 dimensions. Remember that what we just said, that Lorenz transformation is analytic continuation to imaginary angle of simple rotations. So if we have And that helps enormously because you can write without any computations, you can write down the Lagrange function, the action. This was invariant under rotation. Let me write it down in 2 dimensions. The choice of letters is sometimes very helpful. It may, with proper choice of letters in your formulas, you address your subconsciousness actually. And it may help you to find some association, some right association. Anyway, let me write it down as dx ds square plus d tau ds square. Another powerful method of theoretical physics is rewriting the same formula again and again and again.
We can negate the plus sign.
What?
We can negate the plus sign.
It can do what with?
Can turn the plus.
Yes, to minus. Yes, yes. Actually, the answer is square root of. It's convenient to. That there is some constant in front anyway, so I shall write it down this way: minus dx ds square integral over ds. And that's precisely it will be Lorenz invariant. It is also parametrically invariant, which we will address in a moment. And this expression describes, it to be precise, we should put the proportionality sign because there will be the mass coefficient in front, which we will find out. This is the expression in any number of dimensions. It will be simply x here. And it is invariant under Lorentz transformation in the same way as the Euclidean length is invariant. And the geometrical meaning of this Lagrange function is precisely the length of the space-time trajectory. Let's work out a little bit. And as you see, also without external field, the particle moves along the geodesic in Minkowskian space, in Minkowski space. So as I said, Minkowski space is the space where the time comes with the minus sign. And you remember this analogy, so that is this, while x plus so light cone variables are just Minkowskian version of complex variables. Okay, now let's work out. At this point, it seems that it's not clear how it's connected with this thing. It's connected actually in a very simple way. We can always rewrite it in the following way. There are many ways of explaining this, but the simplest way is just let's rewrite it as ds dt ds square root of 1 minus so if you have x and t variables, the trajectory in this space-time develops. You can introduce any parametrization. And this corresponds to one part, by any parametrization, I mean what we already discussed, that this action is invariant under S to f of S transformation. Okay, and this change of variables you can interpret as particular parametrization. Which parametrization do you choose? So you can, by using this, you can choose, you can impose various conditions on S. In particular, well, maybe that's, in particular, you can always choose the parameter S so that T is equal to S. That's another way to deriving the same formula. When you choose T equal to S, you have this thing. And this is now the ordinary velocity. This is the Lagrange function. Well, what would be a non-relativistic limit? What do you think? Suppose we have this is the action for relativistic particle, which you can write down as it's proportional. It's always a proportionality sign here, which we will determine the coefficient of proportionality in a moment. Square root 1 minus v square. I remind you that we set the speed of light to be 1. So how we derive non-relativistic limit from this formula?
We can assume v is small.
Yeah, in comparison with 1. 1 is the speed of light. So if v is smaller than speed of light, we can expand it, and we get v squared divided by 2. And to get the correct normalization, it's a definition of mass, you have to take S, now I'm writing, you have minus m square root of 1 minus v squared dt. And it's approximately proportional to constant plus. So the form of the action is actually determined by symmetry. It's a little more tricky if we started with non-relativistic case from the very beginning. By the way, before I forgot to say that I use this particular parameterization, but in many cases it's inconvenient and you have to use completely different expressions. There are infinitely many different expressions for the Lagrange function depending on how you, it's called which gauge do you choose, depending on how you parameterize things. So there was something I wanted to say here. Anyway, let's also derive this from symmetry in non-relativistic case. Namely, let's decide what is so special about the action mx dot square divided by 2 over dt. What are the symmetries of this action? That we kind of discussed already. But the new thing which I'm going to say now is that those symmetries define the action in the same way as they define relativistic action. So what symmetries do you remember of these guys? And why it cannot be, which symmetry, for example, forbids x dot to the fourth? Or x double dot here? So it's obviously invariant under rotations, right? And under translations. What you need is the symmetry under Galilean transformations. So let's take and see what happens with the action under Galilean transformation. And under Lorenz transformation, this expression is explicitly invariant. Under Galilean transformation, it's slightly trickier. So we see that the new action is m x dot minus v square divided by 2 dt. Okay? So the action changes. We have the old action minus m integral x dot v plus m v square divided by 2. The last term it's just a constant. V is a constant. So it doesn't change equation of motion. So if it was for the last term, the equation of motion generated from S tilde and from S will be the same. Now I claim that they will be the same also when you take into account this thing. Why this term doesn't change equations of motion? This is related to something we discussed in this lecture at the beginning.
It's a total derivative.
It's a total derivative, yes. And so, although the action changes, in this sense I said it's conceptually slightly more complicated than relativistic case. When we perform the Galileo transformation, we obtain a new action, which, however, generates the same equations of motion. Now, imagine, well, we're running out of time a little bit, but that's the last thing I will say. That the symmetry is powerful is clear that if you have x dot to the fourth, for example, then this term coming from this thing will not be a full derivative. So this equation will generate a different equation. This new action will generate a different equation of motion. Okay, let's stop here. We will continue next time.